All right, welcome back, everyone. I keep having this weird issue where Zoom makes me sign in twice. I'm kind of curious if anyone else is having that problem. And it's inconsistent, but it happens most of the time. Either way, not a big deal. We are going to pick up where we left off in the last section of Chapter 6 that we will be testing on. Remember that we're only covering 4 sections from this chapter, and I still need to upload that file that I said I was going to upload. Shame on me. But I will get that. Yeah, let's talk about the test stuff a little bit later. Let's finish 6.5 because we'll definitely finish that. Then we can talk test, and maybe we'll have enough time to start chapter 7 today, maybe. So 6.5, trig equations. We gave you some reminders about the periods of these because this comes up in almost every problem. We went over some basic techniques, some of which have some similarities to techniques when we were dealing with verifying identities. We said to watch out for extraneous solutions, which we have not had this happen yet. Spoilers for today, since it's the last section, or the last couple problems of the section. We said that identities might need to be used. We've talked about how you have to consider the domain restrictions, whether you're going to add that to NPi or NPi or whether you don't. We've talked about when you have to go through n equals 0, 1, 2, 3, all those different subtle details. All right. So if you need any refreshers on that, I suggest that you pull up last classes or the last 2 classes notes. We finished off at example 5. So now we're at example 6. And we're going to solve tan x parentheses cotangent of x plus 1 excuse me, equals 0. That's an ugly misplaced 0. There we go. And we're going to solve this on 0 to 2 pi. So this, again, is a restriction. When you have restrictions, you usually don't have to add the 2 NPi. You usually don't have to go through the n equals 0, 1, 2 stuff. It just depends on if there's any, like if there was a 2 here or a 3 here, then you would have to go through some of those. All right, well, this problem, at least in the first step, is easy because everything's factored. It's already factored. You've got 1 factor here and you've got 1 factor here, and it's already set equal to 0, which is perfect. So we can just go ahead and apply the 0 product rule. So we can do the, was I switching colors? No, I was not. ZPR means 0 product rule. So the tangent of x is equal to 0. Or we can say the cotangent of x plus 1 is equal to 0. We're separating this into cases. Now tangent of x equals 0. You're trying to find all angles that when you take the tangent of that angle, it spits out 0. Well, clearly, since this is a 0, it can't be using either of the 2 triangles, the 45, 45, 90, or the 30, 60, 90, because none of those sides were 0. The only way this is possible is for the quadrantals. That's the only way the tangent can be 0. It's either 0, 90, 180, 270, or 360. So we got to figure out which one it is. So remember that tangent is the ratio of y over x. So remember, tangent is the ratio of y over x for the coordinates. And then when you have your unit circle, boom, 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 boom. So y over x, that means the y has to be 0. It can be 0 over whatever. So the y value is 0 when you don't move up or down, which would be this point and this point, which are 1, 0, and -1, 0. In terms of degrees, that's 0 degrees and 180 degrees. Or, in terms of radians, like I prefer, 0 and pi. Again, tangent is the ratio of y over x. 0 over 1 is 0, 0 over -1 is 0. So those are the 2 points on the unit circle that would correspond to solving this. Well, in terms of angles, that's 0 radians and pi radians, or 0 degrees and 180 degrees. Now both of those are inside 0 to 2 pi, so they're good, and we don't need to add any plus 2 npi because plus pi, because this is tangent. You would add plus npi, but if you take 0 and add pi, you get this solution. if you take pi and add 0, I'm sorry, if you take pi plus pi, that's what I was doing wrong in my head, you get 2 pi, which is already past where you want to be because of that parentheses. All right, cotangent plus 1 equals 0. Let's subtract 1 on both sides. So we get cotangent of x equals -1. So we're looking for the ratio, again, tangent's y over x, so cotangent would be x over y, to be a -1. Well, that can't happen on the quadrantals because one of those is always a 0 and one of them is a 1. So this is going to be one of the little right triangles. So cotangent needs to be -1. So that says that the, all right, tangent is opposite over adjacent, so cotangent is adjacent over opposite. That has to be -1 over 1. Well, let's not focus on the negative for now. If you got your little triangle, that just says the adjacent needs to be a 1, the opposite needs to be a 1. Well, that's the 1, 1 square root of 2 triangle, which makes this pi over 4 for our reference angle. But it's a negative, so this is just a reference angle. We need to put that in the appropriate quadrant. So then we have to come back and say, well, cotangent is negative in quadrants what? Well, it's in the same quadrants that tangent's negative. Well, they're all positive in quadrant 1, and then us smart trig class T says tangent's positive in quadrant 3. So if tangent's positive in quadrant 1 and 3, that means it's negative in quadrant 2 and 4. So we need to put this reference angle in quadrant 2 and 4. So to put this in quadrant 2, it would be like this. This would be our pi over 4, but then our actual angle would be that, which would be pi minus pi over 4. Which is 4 pi over 4 minus pi over 4. So we'll call that x3. So that would be 3 pi over 4. Putting the angle in quadrant 4, however, sorry, that looks a little crooked. It's like a politician doing math. So here's the pi over 4 reference angle now, but the true angle is this, and that solution, the fourth solution we're finding, would be 2 pi minus pi over 4. It's 360 minus the reference angle, which 2 times 4 is 8, so that's 8 pi over 4 minus pi over 4, which is 7 pi over 4. And then we just like to put our solutions all in one big section. So 0 and pi, and I'm going to try and put them in order. So 0, pi, well, 3 pi over 4 comes before pi. So 0, 3 pi over 4, pi, and then 7 pi over 4. Or in terms of degrees, 0, what's that, 135, 180, and then 325 degrees for all of them. Those are our 4 solutions. No plus in pi's. If I didn't have this part, then each of those would have had plus in pi, again, for each one of them. Not 2 in pi because we're dealing with tangent. Tangent is periodic under pi, not 2 pi. So that's the one subtle change that can mess you up, can make you go from having everything completely right to everything, I mean, completely wrong as my math lab says, but on a test, again, if you're showing work and you're emailing me and say, Mr. Beckner, check out question number 3, then I go, oh, okay, you just added the in pi. Not a big deal. Here's 4 out of 5 points, something like that. But practice and get it right the first time so we don't have to worry about those details. So this problem, you did not have to factor, it came pre-factored. That doesn't have to be the case. I could have certainly given you this as a problem, tan x, cotan x, and then plus tangent of x equals 0. And what's interesting is some people would then go, oh, well, this right here, tangent times cotangent cancels each other out, so that's just a 1, because those are reciprocals of each other, and you get 1 plus tangent of x equals 0, and then you're just solving tangent of x equals -1, which you're only going to come up with solutions of the 3 pi over 4 and the 7 pi over 4. You would not get the 0 and the pi. So that's one interesting aspect of solving trig equations. When you have something like tangent times cotangent where they would cancel each other out, you could be removing solutions or possible solutions to the original problem. It's kind of like when you have a rational equation and we say, don't just multiply everything by the LCD to clear it because you might then be missing information, or some people might just try and get rid of the denominator. And they'll say, well, you can't do that because you'll be missing information. And that's kind of the same idea. So you have to be careful with something like that. And that's why I actually would not give you the problem written this way, because someone might go and cancel it and only get half the solutions. And it seems like you're right, but you made something go away that, again, while it can go away, you're removing a complexity to the problem. I'm just erasing everything I wrote above example 6 in blue. Very slowly. There we go. All right, example 7. Will I have enough room? Yes, I will. Sine of x minus 2 sine of x times cosine of x equals 0. Now this minus 2 blah, blah, blah could have been on the other side. And then you'd say, well, it's probably a good idea to just move everything. Now, what I was talking about earlier, I think I may have even said it backwards. I think I may have said instead of multiplying, what I meant to say is you shouldn't divide. So you might say, oh, well, there's a sign here and a sign here. Let's just divide everything by sign to get rid of it. I'm doing something you shouldn't do, because then you're getting rid of a complexity of this. You would only have the minus 2 cosine, and you will end up removing solutions. That's why we never divide out common factors in equations like that. We factor them instead. So again, what I just did was an awful idea. Never, ever, 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 ever do that. You will remove solutions. It goes, again, with the tangent and cotangent canceling, which, again, they do. And yes, technically, you can divide everything by sign, but you're removing too many layers of complexity. Factor. Well, what can I factor? I don't see any sine squares. Well, I do see a sign here and a sign here. That makes it a GCF. So here's a GCF, sine x. So we're going to pop that sine x out, open a parentheses. Then we're like dividing them. We're not doing it on both sides. It's still over here. It still exists. So sine x divided by sine x is 1 minus the 2 will stay. The sines will cancel, and we'll be left with the cosine of x. If you don't trust me, distribute that back, and you'll get the original equation. Now we can zero product rule this. We can set each thing equal to 0. So sine of x equals 0, or 1 minus 2 cosine of x equals 0. So 2 completely different equations. Whenever you see a 0 for just a regular old trig term, that's probably a quadrantal. Sine goes like y. Remember, sine is the y coordinate on the unit circle. We're trying to find y coordinates that are 0, which are, well, coincidentally, the same as setting tangent equal to 0 here and here, which that's 0 degrees and 0 radians and pi radians, or 0 degrees and 180 degrees. Again, that's 1 comma 0, negative 1 comma 0. You don't have to redraw this every time. You can just reference the unit circle. Now, in terms of showing work, this would be excellent for showing your work, because if I just see you go from here to the next thing and all I see is 0, I'm going to go, well, where is you relaying that information to me? If it was pure memorization, that makes it harder for partial credit. If you show me something like this, I can probably scrap together a point or two. So again, x equals 0 and pi based on those 2 points where they're located on the unit circle. Now for the other one, you can subtract 1 on both sides, and you'll get negative 2 cosine of x equals negative 1. You can then divide both sides by negative 2 to get cosine of x equals positive 1/2. Alternatively, you could have added 2 cosine of x and then divided by positive 2. Don't care how you get your algebra done. All I care is that you can get to here. All right, so cosine of x equals 1/2. So here's a reference triangle. There's our x prime, where the adjacent's 1, hypotenuse is 2. Oh, that's the 1, 2 square root of 3 triangle. And that says that x prime has to be, since it's opposite the square root of 3, pi over 3. It's the larger angle. But we need this cosine to be positive. Cosine's positive in more than just one quadrant. Cosine is positive in quadrants, which ones? A smart trig class. So all in quadrant 1, so that's one of them. The reference angle will be one of them. 2, smart for sine, so no. T, trig, tan, no. C, cosine class. Boom. Quadrant 4. So quadrant 1 and 4. And again, that's because cosine goes like the x, and x is positive on the right side of the graph. So x3 is pi over 3 because that's in quadrant 1. But for the fourth one, we need to put the reference angle of pi over 3 in quadrant 4. So here is our pi over 3, meaning that our actual angle is this. So x4 would be 2 pi minus pi over 3, which is 6 pi over 3 minus pi over 3, and that's 5 pi over 3. So far, 1, 2, 3, 4 solutions. I'm going to write this incorrectly. I'm about to write this incorrectly, and I did not give myself enough space, did I? It's going to mess everything up. Hold on, I'm thinking. Still have 2 more. Come on, scroll down, please. Why won't you scroll down? Okay, that's good enough, whatever. Trying to make this work. Boom. And I can get rid of all that. Go away, please. There we go. I don't understand this program sometimes. All right. Let's recollect our thoughts now that my insanity is done. We had our 1, 2, 3, 4 basic solutions, all within 0 to 2 pi. So if you do this, if you box this up and shift it up as your answers, it's wrong. And you might go, oh, well, I must have messed up somewhere here. No, you didn't. Oh, I must have messed up somewhere here. No, you didn't. No, we didn't. These were all accurate answers, but they're not all of them. Mr. Beckner, you just said that was all of them from 0 to 2 pi. Yes, I did. I never said that there were any restrictions to this. Nowhere did I write on 0 to 2 pi or on 0 to pi or pi to 2 pi, whatever. There were no restrictions, which is why this is a terrible answer. We have to add, since we're dealing with cosine, 2 in pi to every single one of them. And the very first one, I'm going to write it, I'm going to erase it. Actually, let me just make a little memo here, actually. For the first one, it's 0 plus 2 in pi. But 0 plus anything is the anything. So that first solution, I'm not going to write as 0 plus 2 in pi. I'm just going to write 2 in pi. So every multiple of 360 degrees, 0, 360, 720, 0, 2 pi, 4 pi, 6 pi, 8 pi. That's what that says. Negative 12 pi, negative 14 pi. That was the 0. Now let's take the pi. So that'll be pi plus 2 in pi, and that's all you can do there. There's no simplification. Then we have the pi over 3 plus 2 in pi. Then we have the 5 pi over 3 plus 2 in pi. No, I did not put these in ascending order, and that's because of the periodic nature we're invoking in here. You could have taken this one and put it second if you wanted it more in a true ascending order, but there's nothing wrong with writing the answer this way. It's frustrating if you had those 4 solutions right and then you get it wrong because you forgot your 2 n pi's. It's just as frustrating if it goes the other way, if you put the two in pies and you weren't supposed to have them. So know when you need them, which is when we give restrictions, and know when you don't. You also need them when you have a problem that had a 2 or a 3 or a 4 or something like that inside of a trig function. We talked about that in a previous class. Go back and watch that again. Look over your notes again if you need reiteration. All right, example 8. We're getting there. We are getting there, believe it or not. Sine squared of x minus 4 cosine of x plus 4 equals 0. Now, I alluded to this type of problem last class. Now, if this was a little different. If this was not a cosine, if this was a sine, I would say just go straight to factoring. If that was sine squared and sine, go ahead and try and factor. But it's not. So what we have right now are two different trig functions, which we generally don't like to have unless it's already pre-factored, or if it's just a GCF that we can take out. But there is no GCF here to take out at all. So what you want to do is use one of your Pythagorean identities, which says to swap out a sine squared or a cosine squared. What we have is a sine squared, so we're going to swap it out for its equivalent. Now, if you don't remember its equivalent, you better know that sine squared plus cosine squared is equal to 1. You don't ever forget this. You don't ever get to forget this for the rest of your mathematical careers. If you move the cosine over, sine squared of x is 1 minus cosine squared. I highly suggest knowing that off the cuff, that cosine squared is 1 minus sine squared, and vice versa. Because we see it so much. So that's the replacement I'm going to do here. So that becomes 1 minus cosine squared of x. I don't need any parentheses because nothing else fancy is going on there. Then minus 4 cosine of x plus 4 equals 0. Well, the 1 and the 4 make a 5. The cosine squared should be the first term, so that's negative cosine squared of x minus 4 cosine of x plus 5 equals 0. And then some of us might be able to go straight to factoring. Me, though, and most students, we struggle with factoring when there's a negative for the leading term. It messes a lot of our common techniques up. So you have two options. Option 1, which I will erase in a second, this is the longer algebraic version, is just move everything to the other side. So you add cosine squared, add 4 cosine x, and subtract 5 on both sides, and that would make the leading term positive. And that's what I tend to do in an Algebra 1, Algebra 2 class. But I'm going to give you the shorter version here. Multiply both sides by -1. So we take -1 times the left, -1 times the right. This will get the same job done. Because a negative times a negative, all these signs will just switch. Now our positive term will be leading. Cosine squared x plus 4 cosine of x minus 5 equals 0, not -0. And then we can factor. We said if you need to see the similar version of this, so we can say this is similar to, you could just use x squared plus 4x minus 5 equals 0, which you'd factor like so. Factor pairs of 5 are 1 and 5, not a lot of options. To make sure that they subtract to a positive 4, you go plus 5 and -1. That means that the factored version of this is cosine of x minus 1 times cosine of x plus 5. Some people don't do any of this side work and still get it right. That doesn't matter. It's whatever you need to do to get it right. And now here we apply our zero product rule, which means we set each factor equal to 0. So we set the cosine of x minus 1 equal to 0. And then we set the cosine of x plus 5 equal to 0. First one, add 1 to both sides, you'll get cosine of x equals 1. And this is only possible on a quadrantal. Tangents are the only ones that are 1 on non-quadrantals. Again, quadrantal, 0, 90, 180, 270, 360, etc. So we're trying, remember cosine is like an x-coordinate for the unit circle. So we're looking for x-coordinates that are positive 1. Well, here's our unit circle. The only time x is positive 1 is at 1, 0, which is 0 degrees or 0 radians. There's only one solution to that. From 0 to 2 pi. You might say, well, hold on, Mr. Beckner, why isn't it this one? Because that point is negative 1, 0, and negative 1 is not positive 1. All right, how about cosine of x plus 5? Well, subtract 5 on both sides. You get cosine of x equals negative 5. Now that is obviously not the unit circle. It's only ones and zeros for the unit circle, or undefined. Okay, well, that's obviously the, all right, well, cosine of x, we can say that's adjacent over hypotenuse. So that means the adjacent is negative 5 over 1. So we need to draw a right triangle where the reference angle has an adjacent of 5 and a hypotenuse of 1. And then we go, well, what is this side? And if you did this, it would end up being 1 squared minus 5 squared under a square root, which is the square root of negative 24, which is not possible. What that means is, it is not possible for the cosine of x to be equal to negative 5. Now, maybe you didn't think to draw up this triangle. There's another way you can determine that too. But because that's not possible, there is no solution to that segment. I'm not saying there's no solution overall, I'm saying it's no solution to this piece. Alternatively, with cosine of x equal to negative 5, I made a statement at the beginning of the section. Watch out for extraneous solutions, mainly an issue with sine and cosine, which are bound between negative 1 and positive 1. Because on the unit circle, the largest that x coordinate can be or y coordinate can be is a positive 1 or negative 1. It means the answers can be no bigger than that, unless you have an amplitude factor, which we don't. And if we did, we would have divided it out. See, cosine is bound between 1 and negative 1, but we have it being equal to a negative 5, which is completely impossible. It is extraneous. There is no solution to that segment. So that's what I mean by alternatively, cosine of x is bound from negative 1 to 1 in the range. Negative 5 is, quote, too big. And by too big, I mean in absolute. The biggest that thing could have been was a positive 1 or a negative 1, and we've gone past that. So no solution. Again, just to that segment. But we still had the 0. So our answer is 0, right? You can say x equals 0, and you box that up and you ship it out, and my math lab tells you it's wrong. Why? Because it's not good enough. Look at the original problem. I don't see on 0 to 2 pi. I don't see any restrictions. This was non-restricted, which means we have to add, since we're dealing with sines and cosines, 2 in pi. So we go, our solutions are 0 plus 2 in pi, but 0 plus anything is just the anything. So in other words, our answer is every 360 degrees, going up or down. 360, 720, negative 360, negative 720, 0, 1080, negative 1080. Keep adding and subtracting 360. Or just in terms of pi, 0, 2 pi, 4 pi, 6 pi, 8 pi, 10 pi, 12 pi, 14 pi. A lot easier to rail through those. Another strength of radians versus degrees. adding 360 degrees over and over can get kind of tedious. So this is the thing to watch out for with extraneous solutions. When sines or cosines are set equal to numbers that are bigger than 1 in absolute. Notice I said in absolute. So your sines and cosines need to be set to things like a half, square root of 3 over 2, square root of 2 over 2, or negative any of those things. Negative 4/5, negative 19/20, positive 11 over a million. But it cannot be equal to 11 or a million or negative 11 or negative a million. Tangents can, cotangents can, secants and cosecants can. Sines and cosines are the only ones that have this very, very tight bounds. What's interesting is secants and cosecants are actually bound to everything outside of -1 to +1. So they can't be between -1 and 1. They're everything else. It seems really weird, but that's because of that reciprocal nature of them. All right, last but not least, and we're going to kind of tie some things together that we did last class just to reiterate them. Too far. Example 9, will I have enough room? Yes. 2 sine cosine equals 1. Now be careful here. Some people will go, what I'm about to do is wrong, I'm going to pull out red for wrong for a second. Oh, well, zero product rule, the left side's factored. So we go 2 sine x equals 1 and 2 cosine x? No, it actually wouldn't be the 2, it would just be cosine of x, because the 2 is already accounted for here, equals 1. But it's called the zero product rule for a reason. They have to be set equal to 0. It's not called the 1 product rule. It's not called the 17 product rule. This is completely and utterly garbage, trash. It's wrong, 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 wrong. You can't do it. This is not the zero product rule. You would need to move the 1 to the other side. You would have to move that 1 over there by subtracting, and then try and find a way to factor this, which I don't see. If you see it, then you're a better trigonometrician than I am. So, I'm stuck because I can't factor this, even by moving the 1. I can't zero product this. If I move the 1, it's not a product, and this 2 is just really screwing us up, as well as the 1 with everything on the other side. These are really messing us up this time. Now, we've had the 2 in front and it not be a problem before, but how it's messing us up here will also be a strength. So let's go back to the very beginning, those instructions. And something we haven't done yet, we have used Pythagorean identities, but we have not used any double angle identities. Now, I said in the real world or a class past this, you may need half angle identities, you may need sum and difference identities. Those are all possible, but in this course, homework tests, it's just the double angle identities that might come up. So cosine squared minus sine squared is cosine of 2x, or 2 sine x cosine x is sine of 2x. I almost said that wrong, I had to think. 2 sine cosine is sine of 2x. So again, as a reminder, and scrolling is going to take forever. There we go. So as a reminder, 2 sine of x times cosine of x is the double angle formula for sine. And I'm about to put the 2 in the wrong spot. Sine 2x. So that entire left side we can just change to the sine of 2x. Is equal to 1. Now this right here is a problem. We should not be solving any trig equations directly with that 2 there. It will throw us off because this is that whole, I'm giving you a problem in dollars, you're going to have to convert it to yen and then go back to dollars in the end. So this is where we had said, and I'm not going to scroll back up and down again because we've already done an example like this, that because of that, we need to do one of those substitutions. We say, let theta, or whatever letter you like, y, I don't care, equal to the inside, which is 2x. So this just becomes the sine of theta equal to 1, which we do know how to solve. Now again, after you've done hundreds of these, you may say, well, I know how to solve it with the 2 there. I can account for that later. And that's up to you. That's your own prerogative. I will even say that when I'm railing through trigonometric equations for whatever reason I kind of do that too. But I will also say that I make more simple mistakes when I don't show my substitution work. So sine of theta equals 1. It's only possible for sine to equal 1 on a quadrantal on its most extreme cases. So we're trying to find on the unit circle where is its y value 1, because sine goes like y on the unit circle. Well, that would be here. That point is 0, 1. Now you might think it's here, but that point is 0, -1, and the negative is not positive, obviously. So that says theta is equal to whatever angle that is, which is pi over 2. And you might box it up and ship it out, and it's wrong. It's very wrong. That is our solution in what I'm calling yen, or pesos, or euros, or pounds, or whatever currency you like that's not dollars. If I ask you a question in dollars, you need to answer me in dollars. I don't want to say, well, how much does that calculator cost? And then you tell me 10,000 yen. Well, I don't understand yen. Give me the answer in dollars, please. Thank you. But here's another issue. With this being a 2, I'm going back to the highlight, with this being a 2, the period of sine of 2x is not 2 pi. It's going to happen quicker because that 2 is a factor that affects the wave speed, as we've discussed. We've said that the period is 2n pi over b, which the 2 here is the b. So what we have to do, even though, so I said this was I did not say this was bounded, so we know that we do a plus 2n pi somewhere. But if you keep going, if you kept going and said, oh, okay, well, this is 2x equals pi over 2, so x is equal to pi over 4, and then you go x equals pi over 4 plus 2n pi. This is what a lot of people will think the answer is, and this is wrong. Because we added the 2n pi to x and not theta, we accounted for the period too late because some other things have happened. This thing was moving faster, and this being a 2n pi does not account for it happening faster. The period is not 2n pi anymore. It's going to be smaller than that. So again, it was critical that we don't add that too late. You add it for the theta. It was also critical that even if this was bounded, we would have to do this anyways, and then just go through the n equals blah, 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 blah cases. So this is our theta, but we said theta is really 2x. So let's go back to the standard American dollar. Theta is 2x, so that's 2x equals pi over 2 plus 2n pi. And then you can just divide each side by half or multiply, I'm sorry, I said that wrong. You can divide each side by 2, or you can multiply everything by a half. That works too, because I know some people, when they divide by 2, that middle one's going to throw them off, even though I've done that many times in class. So let me just show you the alternative approach. Instead of dividing by 2, you multiply everything by half. I'm going to put the 1/2 here because it's kind of squished. So that says x is equal to, these 2's cancel, these 2 cancel, but these 2 stack up to make a 4 in the bottom. So x equals pi over 4 plus n pi, not plus 2n pi. So you still get the primary angle correct, but you would have the period addition wrong. You would actually end up missing half of the solutions, because this says there's another solution every 180 degrees. If you had plus 2n pi, you would think that the solution happens every 360 degrees. So when you add that 2n pi in a substitution problem is critical. Now, I said this was our last example. You could call it, I'm about to do part 2 of it. You could call it example 10. I'm going to call it example 10 just for fun, but you're going to see some similarities. We've done this before already. Same exact equation, but a bounded solution. So that means you would not have the plus in pi there, and you might think, oh, okay, well then just the answer is pi over 4. Just cut out the periodic nature. Unfortunately, it does not work that way. Whenever you have these problems where there is a number that ends up inside of a trig function, this is worst case scenario in my opinion, because you have to add the 2 in pi at the right time, and you have to remember that you can't just cut that out for the boundedness. You actually have to go through the n equals 0, 1, 2, etc. cases. Until you get to a solution that's too big. So x1, which is n equals 0. Some people might call that x sub 0 to match, and that's okay. It doesn't matter the order of them. That's just going to be pi over 4 plus 0, which is pi over 4. Second solution, which would be n equals 1, would be pi over 4 plus 1 pi, which is pi over 4 plus 4 pi over 4, which is 5 pi over 4. And that's not too big. If it was 9 pi over 4, that would be too big. If it was 8 pi over 4, that would actually be too big because it's exactly 2 pi, and that's a parentheses. If there was an x3, you'd be doing pi over 4 plus 2 pi. Now, this right here is a giant clue that the answer is too big. If you add 2 pi to anything, you're already outside of 2 pi. Not even going to show the algebra because of that. So your only solutions would be pi over 4 and 5 pi over 4. I'm going to tell you, but not write. I would suggest that maybe you write it. I'm going to tell you a pretty strong hint. So the n equals 0, n equals 1, how do I know how far to go? Well, I said you go until the answer is too big. I can do you one better. Whatever number is inside with your x is how many n's you need to go through. So we did n equals 0 and 1 because that was a 2. If that was a 4, I would have 4 unique paths of n equals 0, 1, 2, and 3. 4 would be where it would get too big. If that was sine of 12x, I would need to go from n equals 0 to 11. That 12th one would be too big. So that's actually a pretty nice hint as to where to stop. But remember, you only go through the n values if it's bounded. You generally only add the n pi or 2 n pi if it's an unbounded problem, with the exception of problems with numbers inside the trig function. So once again, this number right here, let's say that was a 17, and the solutions were bounded, so you had to go through n equals 0, n equals 1, equals 2. I can tell you that the 17th one is where it would be too big. It always works that way. Now, do you have to know that fact? No, because once you get an answer that's too big, you can tell it's bigger than 2 pi. But you may make a mistake and maybe you're missing one, or maybe you went one too far and you're not paying attention to the size. So again, that's the number that the n starts to become too big. It's just a nice little clue. It's not mandatory, but it is helpful. I went too far back. There we go. So that right there will close out chapter 6. So test 2 is on chapter 6, specifically 6.1 through 6.3, and then 6.5. We are skipping 6.4. Formula sheet provided for you and Canvas that you can download and print. Do not change this at all. Do not add anything to it at all. And you've already seen what that formula sheet is going to look like. I don't want to have to dig it out from my files right now. But if you do go to the last class, I believe you'll see it. And you'll see it in Canvas very, very soon. This will be another MyMathLab test in the ballpark of 15 questions, I think. 15, 18 questions, somewhere like that. The review is already in MyMathLab, just like the review last time. And the test dates are, dramatic pause, the 9th and 10th, right? Yes, 9th and 10th. 11:09 through 11:10. Start at 12 a.m. on the 9th. It will be finished by 11:59 p.m. You must submit work in Canvas in 15 minutes from finishing the test. If you miss the test, you will need a doctor's note, a court note, something significant to get any kind of makeup. I'm not going to just give makeups willy-nilly for this. 2 days is enough time. You have a week to study. Again, the review material is already there. I will update your homework due dates. 6.5, since we just finished it, will also be due on the 9th. And right now, I need to reorder it, but your Chapter 6 review is at the bottom. If you look at this later today or tomorrow, you should notice it immediately under the Chapter 6 homework, just like the Chapter 5 review was under the Chapter 5 homework. I'm gonna, it just, when you make this visible again, that's how I want to say that, it just defaults to the bottom for some reason. And I did this literally 2 seconds before class started that I made that available. So your review is in the homework, your test, if you go to quizzes and tests, it is not available yet, but you would find it immediately under where it says test 2, and it would say Chapter 6. 90 minutes, 120 minutes, I haven't decided yet. I'm probably going to stick to 120. But I can still make it 90. Let me go in and look at that again, because I can't remember how many questions I made it off the top of my head, because I made it last week. And a lot's happened since then. Remember, the review is going to be similar to the test. It's not going to be all-encompassing, but it will give you a great idea on what to focus on. So the similarity of Chapter 5 review versus Chapter 5 test is going to be there as well. So if you were someone who did not do the Chapter 5 review, most people that didn't do the review didn't do very well. So maybe that would be some incentive to do it, because most people that did the review did pretty well. Again, most, not all. And if you struggle with Chapter 5, if you haven't picked up all the stuff from that, or at least the stuff that you've seen being repeated over and over and over into Chapter 6, you're not going to do well on this test. If you don't know your unit circle, your smart trig class, your 30, 60, 90, 45, 45, 90 triangles, or just your blatant memorization of the giant unit circle, I have no idea how you're going to do most of this test. This is another no calculator test, by the way. You will have plenty of answers that are going to have square roots of 3s and square roots of 2s, and if you type 1.493 or round it, it's going to be wrong, and I won't give partial credit for that, because I'm going to say, well, you're using a calculator, obviously. I should just give you a 0 for the test because you're not following rules. Ooh, you don't want that to happen, do you? Don't be slick. All right. So if you have any questions past that, you can ask them in the chat or email me. Remember, the review is not going to count as a grade. That is just there for you to have something. Okay. Save. I don't think I have. Is this something I want to use? No, that's old. That's what I thought. Okay. So with that being said, we do still have about 20 minutes of class left that we need to use. So we are going to dive into the next chapter. So chapter 7. Let me hit enter 10 million times first. This is going to be a long section. Let's go in the center. This will be 7.1, the law of sines. The law of sines. So we are now going to journey triangles that are not right triangles. Remember, a right triangle has to have a 90-degree angle. A triangle that's not right does not have to have a 90-degree angle. We call those triangles oblique. Not oblique like our abs, just oblique, it's just another word. So oblique triangles do not have a right, which is 90 degrees. They're just whatever. One of them can be 10 degrees, the other can be 20 degrees, and the other is 150 degrees. Or they could be 60 and 60 and 60. Or they could be 60, 70, and 50. I had to think about that for a second, yeah. You don't have to have a 90-degree angle. Now here's the problem. Every single thing that we have learned thus far about sine being opposite over hypotenuse, cosine being adjacent over hypotenuse, tangent being opposite over adjacent, everything we've learned so far has only dealt with right triangles. When you're dealing with things that aren't right triangles, the sine of an angle is not necessarily its opposite over hypotenuse, especially because there isn't even a hypotenuse. There's no hypotenuse. So you can't say sine is the opposite over hypotenuse because there is no hypotenuse. What you could do is you could form an extra triangle out of it and make a right triangle, and then you could say that that thing's hypotenuse relates to a sine. And that might help you in some problems, you know, physics problems, applications, it usually is helpful, but not with most of the stuff we're going to be doing in this section. So chapter, excuse me. So this chapter, we are generally dealing with triangles that don't have a 90-degree angle. Everything that we'll be doing still is valid if it does, but if it has a 90-degree angle, I just go back to the chapter 5 and 6 stuff because it's easier. So when you are dealing with oblique triangles, you need to avoid SOHCAHTOA and Pythagorean identities. Sine squared plus cosine squared is no longer 1. SOHCAHTOA no longer works. But we can still, even in this new world with no right angle, based on some formulas and some problems we're going to give you, we can still fill in all 6 components of information. 3 angles, 3 sides. If you're given 3 of these components, at least one being a side. I'm going to explain why we have to have just at least one side in a couple seconds. All right, so why do you have to have at least one side? I'm going to write some stuff that's going to be erased. Here is a right triangle. I know this isn't supposed to be dealing with right triangles, but just we can still use the explanation. This is going to be the 3, 4, 5 triangle. And then I've got another triangle over here. And this is going to be 6, 8, 10. Now, I'm going to do some stuff. Check my mode. Well, I do have the calculator pulled up, so I'm just going to get to like a 10th or 100th of a degree what these angles would actually be. So if you did inverse sine of 4/5, that would give you the bottom left angle, and my mode is in radians, so I need to convert that to degrees. So 53.1 degrees. So this is 53.1 degrees, 53. Just kind of scroll in. And if that's 53.1, 90 minus 53.1 is going to be 36.9. So then that makes this angle 36.9 degrees, and this is, of course, 90. Well, guess what? With a 6, 8, 10 triangle, this is the exact same ratio of them. So this angle is 53.1 degrees, and then this angle is going to be the 36.9 degrees, and this is still a right 90-degree angle. Why did I just draw these two triangles? And if you don't trust me, if you do the inverse sine of 8/10, inverse sine 8/10, you can see that that angle is 53.1, blah, 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 blah. The point is, this angle is the same as this angle, and then the blue one's the same as the blue one, and the right is the same as the right. So if I give you this problem, and I say this is 90 degrees, and I say this is 53.1 degrees, and I say this is 36.9 degrees, and then I ask you, what are the legs A, B, and C? You can't tell me, because it's possible they're 3, 4, and 5. It's possible they're 6, 8, and 10. It's possible that they are 9, 12, and 15. It's possible that they're 30, 40, and 50. It's possible they're 300, 400, and 500. There are infinitely many answers. If all I give you are 3 angles, there are infinitely many answers because of what we call congruent triangles. If their angles are the same, the ratio of their sides are the same, so there's infinitely many of those little right triangles I could make if I only know the angles. But by knowing one of the sides, that forces your size to be very specific, which is why you have to be given at least one side. I will not give you a problem where I just give you 3 angles. That will never happen in here because you couldn't answer the question. I said I was going to erase that, but actually I'm going to leave it. I kind of like that up there. So again, you have to be given at least one side. Now there are several cases that we're going to be going over in the next couple of days. And they're all based on how many angles you have, how many sides you have, and what order they're in. So we're going to be using the letter A for angle, and we're going to be using the letter S for side. So we need 3 pieces of information. So the different cases are, we could be given 2 angles and a side. We could be given 2 sides and an angle, or we could be given 3 sides. Now, while you can't be given a problem with 3 angles, you can be given a problem with 3 sides. In this section, we're going to focus mainly on the problems where it's 2 angles and a side. Those are the easiest cases. That's what we're going to focus on at first. But then we're going to focus on the 2 side case, and we're going to talk about why it's weird, how it's weird, and what we can do to account for it. So the 2 easier cases are angle, side, angle, side, angle, angle. Angle, side, angle, or side, angle, angle. So imagine you had a, it's going to look equilateral, but don't pretend or don't imagine this is equilateral, and don't imagine that it's 90 degrees. I'm just drawing up 2 triangles, and I'm going to show you what is given. So in blue will be what is given. So angle, side, angle means that this would be known. So we'll know this angle, then we know this side, and then we know this angle. And it doesn't have to be bottom left, bottom right, and bottom. It could have been this angle, and this side. That would have been perfectly fine as well. I'm just saying that everything is kind of in a wedge like that. And then side angle, angle might go something like this, you know, this side, this angle, and this angle. But you think about yourself going clockwise or counterclockwise to pick them up. So side, angle, angle, or side, angle, angle. It doesn't matter which order you go. An extra little blue dot there. Side, angle, angle. The easiest cases are when you have two angles. This is always true. The easiest case is always when you have two angles because you can always find the third by the fact that triangles add up to 180 degrees. Their angles are, you don't call them supplementary. Supplementary is just two angles that add up to 180, but it feels like that. So these will always have one solution, just one solution. And the order that you should handle this stuff is, why is it not doing one line at a time now? Start by finding a third angle. All angles of a triangle sum to 180 degrees. So you can just do 180 minus the other two, or you can say the three add to 180 and do your algebra, whatever you like. So if you have two angles, the first thing you should do is find the third. Super easy. You could have done that before trigonometry class, I hope. If I tell you one of the angles is 10 and another angle is 20, you do 180 minus 10 and 20, which would be 150 to get the third angle. If I tell you one of them is 100 and the other is 70, you do 180 minus 100 minus 70, and the other angle would be 10. After you have your third angle, you will use what is known as the law of sines. Find the remaining two sides. The law of sines is as follows. And this is for any triangle in general, but we really only want to use this for oblique triangles. If we're dealing with right triangles, don't do this. You are making this much worse than it has to be if your triangle is right, if it has a 90-degree angle somewhere. All right, so the law of sines is A over the sine of A, little a and big A. Little a is going to denote lengths. Capital A will denote angles. So this is equal to B over the sine of capital B. But it's also equal to C over the sine of capital C. Now, I really don't like using C's because lower and uppercase C's look the same. So this, what I'm about to write is the exact same thing, just using Greek letters. Little a over the sine of alpha, so alpha is angle A, capital A, equals little b over the sine of beta, which basically looks like a B already, and then little c over the sine of gamma. So the left black version is with traditional letters, the blue Greek version, I'm sorry, the blue right version uses some of the Greek letters. So again, for our standard triangle, if this is side A, this has to be angle A. If this is side B, this has to be angle B. If this is side C, this is angle C. But I really don't like doing that because capital and lowercase c's look the same. So alternatively, in Greek, you can go A, B, C, and then this is angle alpha, angle beta, and then angle gamma. Gamma just looks like you took alpha and rotated it 90 degrees. Kind of looks like a Y almost as well, like a cursive Y. Now you might be thinking, Mr. Beckner, what in the world is this? We've never seen an equation with three sides. Equations are supposed to have two sides. And you're right, equations are supposed to have two sides. All this says is that the ratio of the length of one of the sides to the sine of its appropriate angle opposite of it is the same no matter what pair of information you're using on a triangle. What you do is just pick two of these. Maybe you just want to use the A's and the C's, so you ignore the middleman. Maybe you want to use the B's and the C's, so you ignore the left one. Or maybe you want to use the A's and the B's, so you ignore the right one. That's all you do. You just pick two. Length over sine of angle, length, sine of angle, length, sine of angle. This is a very easy formula to remember. Ultimately, length, sine of angle. Now, the cool thing is you can actually get this upside down. You can go sine of capital A over A equals sine of B over little b equals sine of capital C over little c. That is the same thing. And then you just pick two of the three and ignore the third or whatever. However, the algebra that we'll be doing for most problems, it's just a little easier if you have the side length in the top and the sine of an angle in the bottom. So while they're interchangeable, I will stick with this version. However, if you memorize it, which you have to memorize it for the Chapter 7 test, if you memorize this upside down, no one's ever going to care or know as long as you can get the math correct. I will mix up between using traditional letters and Greek letters. You have to get used to the Greek letters. You will see them later in your life in calculus and in this class. All right, I'm trying to think. 7 minutes. It's a real tight squeeze. I tell you what, we're gonna stop here. I don't think I can finish example 1A in 7 minutes, and I don't want to start it and leave us hanging. So we're gonna go ahead and call it there. When we come in next class on Wednesday, we will pick up where we have immediately left off. You'll see the formula, and then we're going to dive head first into these problems. Again, we are opening a whole new world here. Up until right now, we have been stuck using triangles where one of the angles had to be 90 degrees. There are tons of triangles in the real world that aren't 90 degrees. A lot of people like to talk about triangulating coordinates. And the whole idea of that is, you know, someone's here, you know, someone else is here, and then you just find an angle between them. You find that angle alpha or whatever you want to call it, and then you have this distance, and boom. Or maybe you don't have those particular two sides. Maybe it's this side and this side, or this angle and you have this angle. But you can do lots of things in the real world with this triangulation using law of sines and spoilers for later, law of cosines, that are extremely applicable, and nowhere is there a right angle. Like, oh, somebody gets lost in the forest, but they have a little transponder, so they got a signal reader here and a signal reader here, and they can find the distances between those two, and once they know those distances, they can calculate that angle, and then you can figure out exactly how far to track in. Ships lost at sea, same thing, etc., etc., etc. All right, so I won't rant anymore. If you have any questions, you can email me as always. Like I said, I'll get those homework due dates for Chapter 6 finalized. I'll have the review immediately under the Chapter 6 homework, and then start studying and getting ready for that test. All right, have a good one. We'll see you Wednesday. Take care, everybody.